Okay, so we started talking about this yesterday, and hopefully you've got these key terms figured out here. I'm going to zip through what we've mostly talked about. Rotating a rectangle produces a cylinder, and rotating a rectangle when the axis of rotation is in the middle produces again a cylinder here, but this time the one dimension, right? This dimension on the bottom, as opposed to this door that we look at, where the bottom rectangle here is equal to the radius of the cylinder. In this case, when we rotate the card, the bottom dimension here is equal to the diameter, right? Because we just moved the axis of rotation. And then we had the sphere, right? And we had the cone, that was all covered, okay? And we got to the point where we were stacking. So when we're stacking here, this idea of putting one pancake on top of another, if they're congruent pancakes, completely congruent all the way up, and perfect circles, then they would form a cylinder, right? If we stacked a square pancake and they were congruent pancakes and they were, stacked directly above each other, and they were perfect squares, they would be a rectangular prism. Now, if the height of that prism, as we stacked them up, if the height matched the dimensions of the base, then you would have what you might even think of as a cube prism, right? A right cube or a right square prism, and we call that a cube, right? When it's all the dimensions, both the sides of the base are congruent, right? So we end up with this being a square down here with right angles. And then as you stack them up, so imagine I've got one here, right? I put one right up on top of it and on top of it and on top of it, and I keep just placing them on top like this. And if the height here ends up being exactly the same as these dimensions, then we end up with a cube, like in a rolling, like a dice that you might have. So then when we stack triangles, we get the same thing, where if we stack them on top of each other, we get a triangular prism. So triangular prism here, rectangular prism here, and a cylinder. Now the question is, which ones are right and which ones are oblique, and just kind of keep in mind, here I have, imagine this is a pancake, right? So it's a perfect circle, but it's, sitting on a plate, and the angle we have makes it look like an oval, but it's really a circle, right? So then if I put another pancake directly on top of it so that it's just going straight up perpendicular to the base, and if I were to keep doing that, right, and I were to put another one here right on top, as long as we went up in a way that was perpendicular to the base, and this is getting ugly, but as we went up this direction stacking the pancakes, as long as this is perpendicular, then that is a right cylinder, right? And then if I'm going to try to draw out, this is really hard for me, but I'm going to try to draw these same pancakes. Now they're being stacked, but they're just off from each other, off to the side. And if you kept doing that, and you just kept stacking them up and up and up so that they raised up diagonally, well, then that would be your oblique, right? Oblique prism. Or, I'm sorry, oblique cylinder. So, just keep that in mind as you look at these. You have right and oblique cylinders, and you have right and oblique pancakes, and you have right and oblique rectangular prisms or cubes, and you end up with right or oblique triangular prisms, right? They can be either way. Okay? All right. And here we have them not stacked, but translated, right? So translating, you can see this triangle starts out as a base. It gets translated through space. It ends up here, right, up above. Now the bases, top and bottom, are congruent, and that forms a triangular prism. And here's let's see if I can kind of help point out, this is our face, right? The lateral face is this side over here. If you were to touch it, right, it goes like that. That's a lateral face. We also have a lateral face over here on this side. All right. And that's a lateral face here. So we have the bases, right? And then here we have the in the back, across the back, this side, we just imagine that's the back. Okay, that is a third lateral face. So each side of our figure, right? So this is a triangle, and this is a side of the figure. That tells me how many lateral faces I'm going to get, right? If I have 3 sides, I'll have 3 lateral faces as that goes up, right? And not only that, but if this is a right angle, then these lateral faces are what? They are going to be rectangles, right? Possibly a square, but more likely a rectangle, right? It all depends on how high up you go and whether that matches the bottom and everything else. But you're going to have right angles if it's a right prism. Okay, so if the translation is directly perpendicular to the base, then we're going to get a right angle here, and it'll be a right prism. Okay, so it asks us this question: what is the shape of each lateral face of the triangular prism formed by this movement? So we're going to go ahead and I'm going to go ahead and just try to put in some answers here, right? So the face of the lateral edge of the prism is, where's my tool to add text? There it is. So each lateral face is a rectangle, right? Okay, what is the name of the rigid motion used to create the polyhedron? So to create this three-dimensional solid, the name is a translation, right, of the base. Okay. All right, now we're going to get into using isometric paper here, dot paper. It says translate each triangle to create a second triangle and use dashed line segments to connect the corresponding vertices. So they want us to translate this one diagonally. So what I'm going to do is I'm going to, let's see if I can do this. I'm going to go, so if I go diagonal from here, I'm going to get to there. I'm going to do that twice. So diagonal, diagonal. So this is the new point here, and the dotted line. Let's see if I can make a dotted line look okay. Okay. Actually, I think I have a better tool for this. Let me just see if I can just do a line like this. Okay, that was a little too thick. So I'm gonna keep doing it, but I'm gonna make it much thinner. Okay, so this one's gonna go up diagonally, so it's right there. Right, and then this one diagonally, so it's right there. So we like having this isometric paper because it sure helps us to make much better drawings or sketches of a three-dimensional solid, right? So this is going off diagonally, so what we're going to say is that this is not a 90-degree angle, therefore this is not a right triangular prism. Now, you can see there's a couple different ways to look at this, like it's going up or it's going back. This is the back, this is the front. This is the bottom, that's the top, and it's coming up, or that's the bottom and this is the top. There's a bunch of different ways you can kind of look at this, but as long as we assume these angles that it's going out at are not 90, then it is not going to be a right prism. It's going to be a oblique prism. So go ahead and try to do that, okay? And see if you can do this one in a diagonal, and then we'll do this one vertically. So I'm going to work on these, and I'd like you to be doing that as well in your book. So I'm going to go diagonal here, and I'll do it like this. Oops. Alright, so from there to there, diagonally through 2. 1, 2. Notice I can just move the vertices. So So I go 1, 2, and now we have a right triangle. Right? That has been translated. Now here's going to be a vertical translation. So a vertical translation is going to be easier to see this as a right triangular prism now, as opposed to an oblique one. Okay. Connect these guys here. So this one, because it goes up 90 degrees, if I measured this and if this here was exactly 90 degrees, then we would have a translation directly up. So this would be, where the bases, top and the bottom are the bases, and the sides are the lateral sides, right? Lateral faces and bases is what we have. And since the lateral bases come up perpendicular to the base, the lateral faces are perpendicular to the base, then it is a right prism. And we can see that a little bit clearer here. Thinking about the sides here, if we go diagonally, you can see, since this angle is, I'm going to freehand this one here a little bit. So this angle here would be acute, right? And this angle here would be obtuse. And what we end up with is we do not end up with right angles on this lateral face right here. If I look at this lateral face. So this lateral face would be something more like a parallelogram, and we know it's a parallelogram because we know these sides are congruent, and we know these two sides are congruent, because the translation, is taking the object and translating it a fixed distance. All the points are translated the same fixed distance, so the length of the translation, the length connecting of the line or the segment connecting the pre-image to the image, right? Here and here, those two have to be congruent. These two have to be congruent. We have congruent opposite sides. We have a parallelogram. And then because this was not 90, it's not a rectangle, so it's just a regular parallelogram. Whereas these faces would be a rectangle, right? These faces. Okay. Go ahead and get those drawn. And here is a horizontal, so we'll do that too. And I will go back to using straight line. So 1, 2, 3, 4. And I'll go back 4 dots. 1, 2, 3, 4. And here we go. 1, 2, 3, 4. Now I can connect these guys here, here, and here. And this would also be, this view maybe doesn't look like it, but if I'd gone horizontally with it, then I should have a right angle in here, indicating that this is a right angle here, right? So if this is a right angle in the base as we came up from it, then we would again have a right triangular prism. Okay. All right, so here we go. When you translate a triangle through space in a direction that's perpendicular to the plane containing the triangle, the solid formed is a right triangular prism. Okay. When you translate a triangle through space in a direction that is not perpendicular, solid formed is an oblique triangular prism. There's a picture of an oblique. So now here we go. What is the shape of each lateral face of an oblique triangular prism? It is a parallelogram. Okay. Suppose you and your classmates want to design a cake with rectangular bases. And imagine the bottom rectangular base is translated straight up to create the top rectangular base. Now the shape of each lateral face, since we went straight up perpendicular to the base, so those are right angles everywhere. Here's a right angle, etc. So this, each lateral face is a rectangle. And this would be called a right rectangular prism. Okay. All right, so now it says, draw a rectangle, translate it diagonally. All right, I'm going to do this fast, I hope. Here we go. So I'm going to, let me make sure I've got that. Yep, on the line tool. So here we go. I'm going to start by making a rectangle that is, I don't know, 5 dots this direction and up there. And then we'll go 5 dots that direction and down here. And I will translate it diagonally. Okay, so we analyze the drawing. So now this looks like a regular box, right? So it looks like a right rectangular prism. But the trick here is to keep in mind that our rectangle that we drew here went at a diagonal. So these are not right angles, right? Again, this can be hard to see. I know I struggle to see it sometimes. Right? It's kind of up to you whether or not you can see it. But you got to imagine this is not, that's an acute angle, and this is an obtuse angle, right? So this lateral face, because we went diagonally, so this lateral face, let's see, here, connecting our two triangles, this is maybe the best way to see it. That shape right there is going to be a parallel or a parallelogram. Yeah, parallelogram. Yes, this face right here is a rectangle, but this face right here is not a rectangle, right? Because this one and this guy, that's obtuse and this is acute, and it's going up in a diagonal direction. Okay, so here we go. What do you notice about the relationship among the line segments connecting the vertices in the drawing? So the line segments are parallel to each other. The line segments are congruent. They appear to have the same slope. So they are parallel. Okay, and what two-dimensional figure would you translate to create a cube? So to get a cube, what would we need? We would need a square. They want us to sketch that. So here we go. So I'm going to start with a square as best I can. Oof, I should have used the line tool, not the freehand tool. And then this has to go translated 90 degrees. So what I'm going to do is I'm going to make it just off from 90 so we can see it a little bit. But then these faces all have to be lateral. I'm sorry, they all have to be parallel, and the distance there has to be congruent. Oof. Yeah, I definitely, well, it says to sketch it. So maybe yours is as bad as mine. But there's an example of a cube. Now we have 3 dimensions here. So let me see if I can highlight the 3 dimensions for you. So we have this dimension here, right, that we can measure. Okay, then we have this dimension here that we can measure. That would give us, you know, a second dimension, and then we have a third dimension over here, right? So to find volume, we're going to get that later on. We realize that we have started with a square, but when we translated it, we added in. So the square had this measure and that measure, right? And then when we translated, we gave it a third dimension. We went, went in another direction. So it says when you translate a rectangle through space in a direction that is perpendicular to the plane containing the rectangle, the solid formed is a right rectangular prism. Okay, when you translate a rectangle through space and a direction is not perpendicular, then the solid formed is an oblique rectangular prism. All right, identify the shape of each lateral face of an oblique rectangular prism. So that would be a parallelogram. And I'm not going to sketch that. I think we've sketched enough of those. Now we have, suppose you and your classmate want to design a cake with circular bases. Right? So these look like ovals, but they are represented as circles. Okay? So we have circles, bases. If we go straight up, so now if we're saying straight up, then that means that we've got a right angle, right? So get that line tool back. So this would be, if it's straight up, then it is perpendicular to the base, and that's 90 degrees. Therefore, this angle to the base measures 90, right? So if it measures 90, then we have a right cylinder. So identify the shape of the lateral face of the solid figure formed by this translation. All right, let's think about the lateral face here. I'm going to get a different color here. So if I were to think of this as a soup can. Oh, wait. I don't want that. Let me erase that, or let me undo. I don't know how to do that. Let's hit erase, and let's try it again. Okay. So now, if I think of this as a soup can, and think about this as the wrapper on the can, the wrapper follows around the top, and it appears to have a curve, right? Because it follows around the side, and we would have, you know, this whole face that wraps around the can like the wrapper does is the lateral face. So now let's think about the shape of it. So imagine that I had a pair of scissors, right? And I'm going to cut down that lateral face right down like this with the scissors, right? And when I get done, I unwrap the wrapper. And what shape do I end up with? I'm pretty sure this is on a test too. So the lateral face, oh boy. What's going on here? Okay. The lateral face of this, I'm kind of stuck. I don't know what's going on. I don't even know if it's recording right now. Oh my goodness, I've been zooming for some reason. Let me zoom back out. I'm going to pause this and get this straightened out. I don't know what's going on with my computer.